Section 3.2 Notes, Domain and Range. In this section, you're going to find the domain of a function defined by an equation. Then we're going to learn how to graph piecewise defined functions. Finding domains of functions. When a function f whose inputs and outputs are real numbers is given by a formula, the domain is the set of all inputs for which the expression is defined as a real number. The range is the set of all possible outputs. When an input results in a non-real number, we say that the function values does not exist and that the number being substituted is not in the domain of the function. Think restrictions because a domain will be restricted later on. We also need to be mindful of the application problems as well, because algebraically the domain may not be restricted, but in the real world examples, it may not be physically possible or meaningful to not restrict the domain. So simply put, the domain is the set of a function inputs found on the horizontal axis, so it's basically the x values. The range is the set of a function's outputs found on the vertical axis or the y values. Here is an example. We can find the domain of a function or a relation, and we can find the range for a function or a relation. Finding the domain of a function as a set of order pairs. Let's say we have this function defined with these ordered set of order pairs, and we would like to find the domain. First, we're going to identify the input values. So let me just remove that. The input values are the x values. So here are the input values. I'm highlighting them. So our domain is going to be the set of the numbers. So you have to put it between curly brackets or braces. And you have to list them with a comma in between without repeating. So the set is 2, 3, 4, 5, and 6. Simply put, that is how you're going to find the domain of the function. We're going to focus on the domain of functions for now, and we're going to learn some techniques on how to apply that or on how to identify the domain of a function. So that is if the function is given in a set notation. But if the function is given with an equation form, this is how we're going to find the domain. First, you're going to identify the input values. Next, you're going to identify any restrictions on the input and exclude these values from your domain. Meaning, you're going to find any number that is going to make the function undefined or the expression of the function undefined, and you're going to eliminate these from the domain of the function. Next, we're going to write the domain in an interval notation or an interval form if possible. Here is an example. If we would like to find the domain of the function f of x equals x squared minus 1, as you see here, the input value shown by the variable x in the equation is squared, and then the result is lowered by 1. So any real number may be squared and may be then lowered by 1. So there are no restrictions on the domain of this function, and the domain is all of the set of the real numbers. All of the real numbers, we put it in an interval notation like so. We say it's all the real numbers from negative infinity to positive infinity. There are a few techniques that we can focus on together in order to reach the conclusion faster, which is basically looking for the troublemakers in the expression. Meaning, if you see a denominator, so you're going to immediately eliminate anything that makes the denominator 0 from your domain. And I'll show you with examples how to do that. If you have a square root, we are not dealing with non-real numbers or imaginary numbers because those are functions. So any number that we put under the radical has to be positive. So eliminating the choices that make the radicand negative is going to be the way to find the domain or figuring out what makes the radicand positive. That would be the domain of the function, and etc. And those are the most common ones, is the one with the denominator, the function with the denominator, or with a square root. The interval notations. This is a quick review for the interval notation. We know that when we are talking about an inequality, the solution of the inequality, let's say x is greater than or equal to 4, indicating the solution of an inequality such as x is greater than or equal to 4 can be achieved in several ways. We can use the number line as shown below to graph the inequality. And so the array is going to begin from 4 inclusive. You see and notice the closed circle there. And then we move to the right and indicate that we are highlighting all of the numbers greater than or equal to 4. So the arrow has to go to positive infinity. So it begins at x is equal to 4, as indicated by the arrowhead, and it continues to infinity, which illustrates that the solution set includes all of the real numbers greater than or equal to 4. We can use a set builder notation. So we say all of the x's such that x is greater than or equal to 4, which translates to all the real numbers x such as x is greater than or equal to 4. This is what we call a set builder notation, and that is another way to indicate or to show the solution of an inequality. The third method is to write it in an interval notation, which is our preferred method here, in which solution sets are indicated with parentheses and brackets. The solution for x is greater than or equal to 4 are represented as bracket 4 and goes to positive infinity. The bracket indicates that 4 is included in our solution. Comma indicates continuation, and positive infinity indicates that all of the numbers up to infinity, it goes to infinity, are the solutions for that inequality. This is the most useful method that we're going to rely on because we're going to use it in many concepts later on in higher level math courses, of course. Let's look at some examples on how to find the domain and range. The range is usually determined graphically, so let's determine the domain for each of these functions, and then we can decide on the range as well. So with the first function right here, number 1, f of x equals x squared minus 3x minus 10, I do not see anything that potentially could represent a problem, like a denominator or a square root. So potentially all of the real numbers are going to produce an answer or another real number, which means the domain is all of the real numbers. So I'm going to say domain, and all of the real numbers means from negative infinity to positive infinity. And then we're going to discuss the range later. You can basically graph it and you can see where the range is going to be. I will leave that for a later step. Question number 2. I don't see another issue here. I don't see an issue like a denominator or a square root. So I'm going to say the domain is all of the real numbers from negative infinity to positive infinity. Next, if you have a square root, we know that the domain is all of the real numbers that make the radicand positive or 0, even 0. 0 is fine. Negative is the one that is troublesome. So in order to figure out the domain when you have a square root that is not in the denominator, is to set the radicand greater than or equal to 0. So you're going to set 2x plus 6 greater than or equal to 0. You're going to solve that inequality, and the answer is going to be your domain. So we have here subtract x, you end up with 2x is greater than or equal to negative 6. We're going to divide both sides by 2. The division happens with a positive number, so there is nothing that it's going to change here. We get x is greater than or equal to negative 3. On the number line, if you want to graph it, you will put -3 on the number line on an open number line. There is an equal sign, so there is a circle that is closed and indicating -3 is included in our domain. And then this inequality is read x is greater than or equal to -3, which means we're going to move to the right, highlighting everything. So in order to represent that in interval notation, we know the interval starts from -3 included, so we're going to put a bracket, and it goes all the way to positive infinity, parentheses always from the side of infinity because we don't know the answer. We don't know what infinity is. Number 4, I see a troublemaker right here because I have a denominator. So potentially if the denominator is equal to 0, then we have a problem. We have an undefined expression. So I can tell immediately that if x is equal to 3, we are going to have a 0 denominator, which is a problem in this case. So we need to eliminate that troublemaker, which is the 3. If I have a more complicated expression in the denominator, I will make the denominator not equal to 0 and solve it as if it's an equation. So if I have x minus 3 not equal to 0, I don't want it to be equal to 0 because that is what we're trying to avoid. Now we're going to solve, add 3 to both sides of the equation. You will end up with x equals not equal to +3, which means our domain cannot contain +3. How do we eliminate it? I'm going to draw an open number line. I will put the 3 on the number line, and then I will exclude it with an open circle, meaning all of the other numbers are in the domain of that function. So I will begin with the left interval, this interval right here. This interval can be written as -infinity and it stops at 3 and 3 is excluded. The other interval on the right, this one, can be written as from 3 to +infinity, and then we make it union between them, and that is the domain for the next function. So this is number 3 and this is number 4. Lastly, we have two problems at the same time. We have the denominator and we have a radical in the denominator, or a square root in the denominator. So in order to solve this problem, we want the denominator to be not 0, and we want the radicand to be positive. So we can apply the same concept here, except for we will remove the equal sign from the inequality, so we're eliminating the possibility of it being 0. So here is how we do it. We say, in this case, the radicand is greater than 0, and then we solve. The solution is going to be the domain for that function. So if we solve, we subtract 4, we get x is greater than -4. If you represent this on a number line, it will give you the inequality -4, x secluded, goes to +infinity. So from -4 to +infinity, and that is the domain for question number 5.